Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure and honor to welcome Professor KULUMANI Rangaswamy from the University of Colorado at Colorado Springs, who is an expert on path algebras, graph sister algebras, and he will tell us about a very beautiful and important problem of Naimark. So it's a very old problem, which with Mark Tomford, he solved for graph sister algebras. Ranga, it's a pleasure hosting you. It's all yours. Take it away.
Thank you, Peter. It's a pleasure. Thanks for the invitation to give a talk on this problem. And greetings from mountainous Colorado Springs to all of you. One of the earliest questions about the representation theory of sister algebra was asked by Naimark in 1951, and it's now called the Naimark'S problem. His question is that if a C-star algebra has a unique, irreducible representation up to unitary equivalence, is that C-star algebra isomorphic to the algebra of compact operators on a Hilbert space?
Mm-hmm.
And in the immediate years after Naimark's problem, some progress was made. Kaplansky answered Naimark's question in the affirmative for type 1 C-star algebras, and Rosenberg again answered it in the positive for the separable C-star algebras. But attempts by several researchers like Dismuir in 60, Fell, and Grimm yield only partial solutions. And then after almost 40 years, Ekman and Weaver, they used set theoretical methods to show that Naimark's problem is undecidable in ZFC there. So it's kind of, it's almost stopped there. So people were trying for other special classes of algebras. So Tomford and his student Suri, in 2019, they considered Naimark's problem for graph algebras, which are AF algebras there. They left open the question for a general graph sister algebras. So in this talk, our goal is to show how graphical concepts.
Wait, there is a question. Sorry. Adam, do you have a question?
Yes, I would like to ask whether this result of Weaver and Ackermann is really in this sort of generality. Since as far as I know, probably they showed that the existence of counterexample having exactly Aleph-1 generators is independent from ZFC.
Correct. They using the so-called diamond axiom. I'm not a very expert on that. Using the diamond axiom, under that they produce a counterexample of an Aleph-1 generator sister algebra. But you're right. He said that it's independent of. So that basically their conclusion.
So with this additional assumption that we are interested in algebras having Aleph-1 generators, I think this is the precise statement.
Yeah, correct.
Okay. Thank you.
So here we are going to consider the graph sister algebras of arbitrary graph, and we are able to get a solution to that question. Since sorry, this is my son gave me this new kind of thing, so I'm getting used to this. We also consider algebraic version of the Naimark'S problem for Leavitt path algebras. And we also consider describe C-star algebras possessing finite or countably many distinct non-equivalent irreducible representation also, and give some examples. So that's the purpose of this talk. Okay. Just take with me, please bear with me, since I'm going to simultaneously develop ideas for C-star algebras and also Leavitt path algebras, not knowing how much to assume. So please bear with me. The next few slides, I'm saying things which are obvious to you. So a star representation of C-star algebra is a star homomorphism from the algebra to the algebra of bounded operators on a Hilbert space. And a closed subspace of this space called F, if F is the representation, if F invariant, if F of A on S is inside S for all A. And we say this representation is irreducible if the only closed F invariant subspaces are 0 and H here.
Mhm.
The same way, algebraically, a representation of an algebra A is algebra homomorphism F from A to the endomorphism ring of a vector space V. And again, a subspace W is F invariant if F of A on W is inside W for all element A, capital A. And we say that this representation F is irreducible when the only F invariant subspaces are, again, 0 and V, so very similar. The only thing nice in the algebraic case is that if F is a representation of an algebra A, then F can be made a modulo over A by defining for any element A in capital A and element X in V, A times X is equal to F of A of X. In addition, this representation would be irreducible if and only if V becomes a simple module, that is, the only submodules of V are 0 and V. Okay. I don't know why it's the last parts get cut. Okay, maybe now you can see that. Two star representation F1 and F2 are said to be unitarily equivalent.
Sorry, may I ask you a stupid question? Can you go back to the previous slide? Yeah. So why we cannot have the same effect when we consider B of H instead of endomorphisms of V? Can we also say, that H is a simple module, or it doesn't work?
Yeah, I'm sorry, I didn't get you.
I'm just curious if the same observation which you made here in the algebraic setting can be made in this sister algebraic setting, or there is some function analytic obstruction to the same equivalence? Because you have a nice equivalence.
I'm not quite sure. And the concept of a module somehow, making your module somehow was never done. I don't know why. It seems to be a natural way of looking at it, but I have no idea why.
Okay, good. Yeah, thank you.
But probably the issue is about closeness.
Yeah, I know, but is there an issue or not?
I suppose that it is, since, for example, it is like in this invariant subspace problem, you can always generate something without closure, which is invariant. And I think that there would be plenty of submodules, but I'm not sure.
But I concur. I have a similar feeling. I concur with you. Yeah, thanks a lot. Yeah.
Okay. So unitary equivalent to representation means that there is a unitary U from H1 to H2, so that F1 of A equal to U star F2 of A U for all A. Okay. And likewise, algebraically, so I'm planning is parallelly in developing both these. So to algebraic representation, G1 and G2 are algebraically equivalent if there is an isomorphism T from V1 to V2 so that G1 of A is T inverse G2 of A, T for all A, capital A there. Okay. So the algebraic version of a Naimark problem would then be, I would read something like, describe the associative algebras A over a field K over which any two simple F modules are isomorphic. And in this talk, we'll consider the Leavitt knotology algebras, Leavitt path algebras, having up to isomorphism exactly one simple left module. If time permits, I will look at the general associative algebra case, okay? I'm going to have just review the next few slides, ideas from graphs. Many of you may know about it, so please bear with me.
Sorry, I have another stupid question, if I may. But we have plenty of time, so why not? Do you know, it was very interesting. You said that this general Naimark problem is undecidable within ZFC. Can we say the same about the algebraic part, or it's not known, or it's obviously...
The algebraic part we are going to solve completely. There is no...
Aha.
I mean, no, algebraic part for the general algebra, I do not know. I have only a necessary condition. I'll talk about it.
Okay.
But I do not know necessary and sufficient. But I think it's not known not because of any theoretical thing. It's just because of the lack of algebraic techniques to completely solve it. So it's not theoretical difficulty in the associated algebra case.
Okay, thank you.
So a directed graph consists of set of vertices E0, set of edges E1, and maps R and S from E1 to E0. Given any edge E, S of E is called the source, and range of E is called the R of E is called the range. And a path E1 to En is a simple closed path if the end vertex or range of En is equal to the source of the first edge S1, and S of EI, source of EI is not equal to source of E1 for all I greater than 1. If in addition, if source of EI is not equal to source of EJ for all I and j, we call this closed path a cycle there. If there is a path from a vertex U to a vertex V, we write U greater than or equal to V. And a non-empty set of vertices is called downward directed if, given any two vertices U and V, there is a vertex W and paths from U to W and V to W. A vertex is called regular if it emits a finite non-empty set of edges. It's called a sink if it does not emit any edges at all. And a singular vertex is a vertex which is either a sink or emits infinitely many edges there. Okay. And a subset of vertices is called hereditary if whenever U is a vertex in the subset H, and there is a path from U to a vertex V, then V also must be in the set H here. And the hereditary set is called saturated if there is a vertex U emitting finitely many edges and the ranges of all these finitely many edges is in H, then U itself is in H here. And the saturated closure of a set of vertices X is the smallest saturated set containing is it here. So a graph C-star algebra given a graph E is the universal C-star algebra generated by mutually orthogonal projections P sub V one for each vertex V, and also partial isometries with mutually orthogonal ranges S sub E, one for each edge E, and satisfy these three conditions. And likewise, a Leavitt path algebra over a graph E is against the universal algebra generated by the set of vertices V.
Sorry, there was a typo, right, in the conditions for the sister algebra.
Where?
In the condition 1, right? The star should be.
Yeah, in number 1 there is a typo, yes.
Oh, yeah, sorry. Yeah, should be.
Okay, it's 1-0 for us.
Yeah, right. Yeah, right. Thank you. And similar for the Leavitt path algebra generated by the vertices V, which are pairwise orthogonal, idempotents, and a set of variables E and E star, because we don't have to introduce the E star here, because we unlike in the case of Leavitt C-star algebras, so there's an additional ghost edge is introduced, and these conditions are satisfied, subject to these conditions there. Okay. Now, first of all, I'll point out how rather easily the hypothesis that a C-star algebra has exactly one irreducible representation up to unitary equivalence immediately reduces the nature of C-star algebra. Ultimately, you could see that a nice reduction comes out immediately. Suppose the C-star algebra has only one irreducible representation, then it will have only one primitive ideal, namely the kernel of this representation.
Mm-hmm.
On the other hand, Dixmeyer showed that the intersection of all primitive ideals in a C-star algebra is 0. But if there's going to be only one primitive ideal, then necessarily the primitive wave must be 0. So this implies that 0 is a primitive ideal, and not only that, is the only primitive ideal of this C-star algebra there. Then you could see a simple argument will then show that if 0 is the only primitive ideal, then necessarily a C-star E must be a simple, because if there is a non-zero closed ideal I, and you mod out C-star E mod I, any irreducible representation of the quotient will also be irreducible. So that will give rise to a primitive ideal containing I, which is different from 0. That's a kind of argument to reach the conclusion that such a C-star algebra must be simple there. The same way, for Leavitt path algebra, same type of argument. If it has only one simple left modulo isomorphism, then it will have only one primitive ideal, namely the annihilator of this simple left module. And again, as in the case of star algebra, it is known that the intersection of all primitive ideals, which is called the Jacobson radical, is 0. And again, by the same point of view, you conclude that 0 is a primitive ideal. And the only primitive ideal of Leavitt algebra, by the same kind of argument, will conclude that such a algebra has Leavitt path algebra must be simple here. So kind of a nice reduction very easily. Yeah. So
may I make just a quick comment?
Yeah.
Of course, Jacobson radical is 0 for Leavitt path algebras, but this is something which is very nicely computable for path algebras. And for path algebras, so without Konspiger relations, the Jacobson radical is 0 when your graph is acyclic. But when your graph is not acyclic, you can very nicely compute this Jacobson radical in terms of loops that you have in your graph. It's just a comment. You're not talking path algebras, but somehow It is really nice, but for path algebras, which are like, the mother of Leavitt path algebras and graph
Yeah.
sister algebras,
Yeah.
you can really so nicely and explicitly compute the Jacobson radical. Just a comment.
Sorry, I have a
Okay.
quick question.
Go ahead.
So this reference 1, what is the reference for this? It
I'm
is
sorry.
known that
That's
for the Jacobson.
at the end. It's essentially the book by Abrams, Ara, and Silas Molina. The book on Leavitt path.
Okay. The famous Leavitt.
Okay, thank you.
Yeah.
Yeah, I should have written their name. Yeah.
Yeah.
Now, so we are focused now will be on a simple graph system algebras, and we have a nice result thanks to Peterson and Szymanski. Am I saying correctly? Peter? How do I pronounce it? Szymanski?
No, you pronounce it correctly, but the way the letter ni appears is kind of funny, but it's okay.
But they describe this graph structure, which are simple, of course, assuming graph is countable, but countability is not needed at all. It works arbitrarily. So that statement is, if E is an arbitrary graph, and then the corresponding C star algebra C star E is simple if and only if E satisfies condition L, is cofinal, and for every V and every singular vertex W, there is a path from V to W. Very strong. This property we'll be using later on. Equivalently, it satisfies condition K, and the E has no proper non-empty hereditary saturated subsets of vertices here. Now, just a quick reminder about this condition K and L. A graph is set to satisfy condition K if any vertex V on a simple closed path, say C, is also a part of another simple closed path D not equal to C there. And to define condition L, an exit of a path E1, E2, En is an edge E such that the source of E equal to source of one of these edges E sub I, but E itself is not equal to E sub I here. Then graph condition, graph E satisfy condition L means every cycle in E has as an exit in E here. Just a little detour. Why the choice of letters K and L? I don't know.
Interesting. Indeed.
I have a history.
Okay.
Mark Tomford told me. Those who know it maybe confirm it. Or those who do not know it, understand it. It seems Kunz and Krieger introduced in 1980 a condition called condition. They thought it is R1. They wrote it here. This IR1 is supposed to be a Roman numeral 1. But in 1996, Pask and Rubin, assuming this I stands for the letter I, they introduce a condition J as a follow-up there. And then, because they introduce I and J, then 97, they introduce as a follow-up condition K. And then once we have I, J, K, so it's natural to introduce another following condition as condition now. But independently, in the meantime, Kunz and Krieger come up with the condition 2, Roman numeral 2 there. So fortunately, later on, Astrid showed that for graph system algebras, the condition 1 of Kunz-Krieger is same thing as condition L, and the condition 2 of Kunz-Krieger is almost same like condition K there. So focus.
Since we discussed letters, I have a doubt as to the spelling of Renault. I think here is an E.
Where is it?
Yeah. You see?
Oh, I see. Yeah, that's true. Yeah, that's a type of that. I'll correct that up on that too. But poor condition J remains neglected. And nobody
That's
bothered
unfair.
to continue on that. Anyway, that's a story that I heard from my expert on that. So just as Patterson and Shmensky described simple C-star algebras, then Abrams and Orlando Pino described simple Leavitt path algebras, again, similar conditions, graph condition, that condition L is satisfied and having no proper non-empty hereditary saturated subset subvertices here. In this case, E also satisfies condition K there. So these are some of the graph conditions will come in handy for us in describing graph system algebras satisfying Naimark property. Okay. So with that in mind, we are going to now describe how to construct irreducible representation using graphical properties here. So with that in mind, we are going to consider infinite paths, two infinite paths, E1, E2, En, P, and another infinite path, F1, F2, Fn, and so on. They are said to be Taylor equivalent if there exists positive integer m and n says that the m plus ith edge would be equal to Fn plus ith edge of Q for all I. So in other words, after some time, so the graph, they both sign. I'll give you a bunch of, here's an example. Yeah, for instance, these are all paths. These are all paths which are tail equivalent, okay? Now, the tail equivalence among infinite paths is an equivalence relation, and the equivalence class of all paths equivalent to a given infinite path P we denoted by a rectangular parenthesis P, okay? We also consider paths, if suppose there is a sink W, we also consider paths P whose range is W here. So in this case, if P is a path ending at a sink W, and all the paths, we say path Q is tail equivalent to P, means simply Q also ends at W. So since we will be considering infinite paths, and we'll also be considering paths ending in W, we use the same notation, namely, if P is a path ending at a sink W, then the rectangular parenthesis P means the path Q, whose range is also, which also end at W. Okay. Anyway, that's a diagram of an example of an equivalence class of infinite paths. Now, here is the way to construct irreducible. Fortunately, this constructing has been done already by Carlson and Sims. So suppose you start with a path P, which is infinite path, or is a path ending at sink, and you consider the equivalence class P. Let H sub P denote the complex Hilbert space having the infinite path Q belonging to the class as a normal basis. The set of all Q, where Q belongs to its class, that is the orthonormal basis. Then Carlson and Sims, they showed that there is a star representation from C star E to the C star algebra bounded operators on H sub P, induced by defining. How do you define this representation? All you need is define it on the edges and vertices, so that for all edge E and vertex V and a path Q in this class, you define pi P of E operator on Q would be E times Q if the range of E is the source of the path Q. Otherwise, it is 0. Likewise, pi p of E star of Q would be Q prime if Q happened to be, the first edge of Q happened to be E, followed by the rest of the path Q prime. Otherwise, pi p E star of Q would be 0. And likewise, for any vertex V, pi p of V on Q would be Q if V is the source of Q. Otherwise, pi p of V on Q would be 0 here.
Just let me double check real quick. So there's equivalence class. This is tail equivalence, right?
Yes.
Okay.
But it could be for infinite path or for paths and
Yeah. But they're tail equivalent. So okay. Right?
And they showed in further, this representation is actually irreducible, okay, which is kind of nice. So for our purposes, all the hard work is done already by them, by Carlson and Sims. They say, here is a way to construct various irreducible representations for C star of E. All you need is one of getting hold of an equivalence class of tail equivalent paths, okay? Same way for the algebra, lower path algebra case. Again, P is an infinite path. I'm sorry, this is more important. That's really important for us. Namely, they also showed that if P and Q are different equivalence classes, then the corresponding irreducible representation pi q and pi p, they are not univalent, unitary equivalent. So which is great. That's a real punchline that's useful for us. So different equivalence classes give rise to non-equivalent irreducible representation. Now, same way for the Leavitt path algebra case again. If P is the infinite path or a path ending in V, let V sub P denote the vector space having the set of all paths Q belonging to this class as a basis of this vector space. Then Chen in 2015 he showed that V sub P becomes can be made a module, and also it become a simple left module induced by the similar action. Namely, for all vertices U times Q would be equal to Q if U is the source of Q, otherwise it is 0. And for all edges E times Q would be equal to EQ if the range of E is the source of Q, otherwise E times Q is 0. And likewise, E star of Q would be equal to Q1 if E is the first edge of Q. So Q equal to E times Q1, otherwise E star of Q is 0 in here. Again, if for paths P and Q, if the class P is not equal to the equivalence class containing Q, then the corresponding simple modules V sub P is not isomorphic. They are not isomorphic. And some more graphical things. Aaron and I showed that if a graph E contains two closer paths, C and D, having a common vertex, then there will be uncountably many paths which are not pairwise tail equivalent. Okay. Just a quick diagram example here. So here is an example. C and D having a V as a vertex. Now, it's very quick. Let me just quickly outline the argument justifying this. I thank Zach for come out with a very, very nice, elegant proof. I thought it's worth sharing. So we are given two closed paths, C and D, having a common vertex V. Now, for start with this closed path C. For any n, let C to the n denote the path obtained by repeating C followed by C n times. Okay. First of all, observe that C, the composite CD and DC are well-defined paths. You could see that. I could do. I don't have the diagram in here. Let me see whether I could do this. I could. I'm sorry, my hands are shaking. Go do this. So if you go through that, start with V, going this way, going that way. So CD is defined likewise. Start with V, going this way. You can come back. You get DC. So it's a well-defined. So you consider the uncountably many irrational numbers are between 0 and 1. You write each such irrational number as in the decimal form, r equal to, say, n1, n2, n3, and so on. Then you define for each such irrational number an infinite path P sub r, namely C to the n1, D to the n2, C to the n3, D to the n4, and so on. So this gives an infinite path, and this gives rise to uncountably many infinite paths, and by the definition, they are not Taylor equivalent here. So it's kind of a nice, cool argument.
Yeah.
But as a corollary, then we obtain that if C star E has just one, or more generally, only countably many irreducible representations, which are pairwise not unitary equivalent. And likewise, if a Leavitt path algebra has countably many non-isomorphic simple left module, then necessarily distinct closed paths C and D must be disjoint. That is, no two closed paths have a common vertex. So that's a nice first graphical constraint that we get as a consequence of that. I think that's a proof is again fairly straightforward. So let me just move along. So I'm going to consider some more reductions, some more properties on the C-star or C-star algebra having exactly one irreducible representation up to unitary equivalence. I simultaneously consider Leavitt path algebras having only one simple left modules up to isomorphism. Okay. First, so that's our basic assumption. So first conclusion is the graph cannot contain any cycles here. Why? It's a very easy conclusion, because by simplicity, or the theorem of Patterson and Szymanski, we know that the graph E satisfies condition K. So if E contains a cycle C, by the condition K, there'll be any vertex V on the cycle C will also be a vertex on another cycle D, not equal to C. Then we noted that if in that case, there will be infinitely many, uncountably many irreducible representations. And therefore, there will be uncountably many pairwise unitary not equivalent paths, therefore uncountably many irreducible representation. So that's not possible here. So that's the kind of argument.
Sorry, but I don't understand this step. If E contains a cycle C,
yes,
then a vertex V on C is also a vertex on another cycle D. How do we know it?
That's by theorem of Patterson, and because it's a
What's
simple
the
theorem, by simple C-star algebra, wherever A back we showed that the theorem of Patterson becomes that it satisfies the graph. If the graph C-star algebra is simple, then the graph E satisfies condition K.
Okay.
Condition, okay, which means simply any vertex or a closed path, in particular a cycle, will also be a part of another cycle.
Okay. So there is a theorem. Yeah.
There's also that theorem also mentioned that if C-star algebra is simple, then given any infinite emitter W, and there is a path from any vertex U to W. Okay, that's also a very important property. It's a part of that theorem. So as a corollary, we could conclude that the graph cannot have any infinite emitters. It's row finite. Reason is, if W is an infinite emitter, and suppose E is the edge emitted by W, and the range of E is U, then by Peterson-Saminsky's theorem, there is a path from U to W. So you start with source of E. So E followed by the path will give rise to a closed path. That's not possible because lemma 7 says there is no cycle, in particular no closed path either. Okay. So in summary, what are the graph properties we have concluded, assuming that a C-star algebra has this Naimark property, likewise a Leavitt path algebra has the Naimark property. Namely, we know that C star E and likewise L of E is a simple algebra. The graph E has no cycles. It has no infinite emitters. It's downward directed. And E0 and the empty set are the only hereditary saturated subsets of E. If E contains a sink W, then all paths in E, they end at W. If E does not contain a sink, then every path in E is on an infinite path, and there's only one tail equivalence class of infinite paths in E. Okay. So these are the graphical properties that come as a consequence of our assumption on C star E and likewise on LKE here. I'd like to squeeze out one more graphical property. It's very important, which will then lead us to the main theorem that we want. Okay. So for any vertex V, we define the tree of V to be all the vertices W, so that there is a path from V to W. Okay. We say a vertex V is a bifurcation or is a bifurcating vertex if it emits more than one edge, so at least two or more edges, like in this example there. Okay. A vertex V is called a line point if the tree of V contains no bifurcating vertices and no cycles. In other words, if T of V becomes, if we add all the edges connecting the vertices in the tree, then T of V becomes a straight line path, like V, V1, V2, and so on. Okay. So just a one straight line segment. If there is a sink in the tree V, then the tree becomes a finite path. So in particular, a sink itself is an example of a line point. Okay. So our main propositions is that if C star E has exactly one unitary equivalence class of irreducible representations, and likewise, if 11th path algebra has only one isomorphism class of simple modules, then the graph contains a line point V, and not only that, because of simplicity, the set of vertices is the hereditary saturated closure of the tree of V. This, I'm skipping the proof because it's a little more involved, but let's take a little faith in here. So let's consider as a case of a line point V and look at the tree of V. So it's going to look like this. We wish to construct a set of matrix units in C star of E. So remember, we are under the assumption that C star of E satisfies the Naimark property. So the graph E satisfies all those conditions that we have listed earlier. So because of proposition 10, we know the graph E contains a line point. And I would like to construct using this tree of V a set of matrix units. Just a quick reminder. Set of elements E sub alpha beta. Alpha beta belongs to a indexing set lambda in C star E, likewise in LKE, is called a set of matrix units if E star of alpha beta equal to E sub alpha beta, and E alpha beta times E gamma delta would be E alpha delta if beta equal to gamma, otherwise it is 0. So in our situation, we now started with the tree T of V. Let lambda be the set of all paths F1 to Fn in the graph, so that the range of the last edge is a member of the tree of V, but the previous vertex, the range of the previous edge, R sub Fn minus 1 is not. In other words, the path meets the tree of V the last only once, the first time at F sub n. For each pair of natural numbers, including 0, with I less than j, we define mu sub ij to be the part of the path T of V from V sub I plus 1 through V sub j. Okay, we denote that part of the segment of T of E by mu sub ij. Okay, and also define mu sub I to be equal to Vi. Okay. So with that notation, we define for all members alpha beta in the set capital lambda, E sub I alpha beta to be alpha mu sub ij beta star if range of alpha equal to V sub I and range of beta V sub j, and I is less than or equal to j there. Okay. Like for instance, here is that example. See, this is the tree, the bottom. So alpha is one path, beta is another path. So E sub alpha beta is simply alpha followed by that portion of T of V from Vi to say Vj, and then beta star there. That is when I is less than or equal to j. If I is greater than j, then we define V sub, for that V sub alpha beta to be alpha mu ji star beta star, where range of alpha is v sub I, range of beta is still v sub j there. Okay. Then so that's this example, just illustration there. Then one can show that the set X of all E sub alpha beta, where alpha and beta ranges over are the elements of capital lambda, is a set of matrix units in the C star algebra, C star of E, and also if you consider inside the Leavitt path algebra, also inside LK of E. And because E0 are the only hereditary saturated subsets, or the empty set and the whole set, the closed ideal generated by these matrix units would be the whole of C star algebra, the entire C star algebra, C star of E. So C star of E is the closed ideal generated by this set X of matrix units. And likewise, again, because there is no proper hereditary saturated subset of vertices, the ideal generated by these matrix units in a Leavitt path algebra is also the whole of the Leavitt path algebra there. And this is a very, very useful property, because this then we are almost ready to reach our conclusion, thanks to the work of that I'm going to indicate. Why do we need this result? That's because of Rayburn in 2015 showed that if a closed ideal I of a C star algebra A is generated by a set of matrix units, say X, alpha, beta, then I is isomorphic to the C star algebra of all compact operators on a Hilbert space H, having the set lambda as an orthonormal basis there. So that is the crucial result.
Question?
Yeah, go ahead. Go ahead.
Yeah, since you mentioned this result by Reborn, and you are mentioning the date that this is from 2015, but I suppose that if it is corollary A9 remark A10,
That's
that,
his book, really.
yeah, exactly. So how old is this result?
How old do you mean?
How old is this result? Is it really
I
a new
don't
result?
know.
Like,
It's a good question, because
yeah, go ahead.
it also seems to me that this must have been proven much earlier than 2015.
exactly.
It's possibly. This is from the book I'm quoting. He didn't give the authorship of this result or indicate. Okay, let me take a quick look. I
Okay.
have the book here with me. I don't think he gave the. This is the book. Graph.
Rayburn, yes. We all know this book, yes.
No, see,
The
this is
silver book.
he writes it. I did see he gave attribute the authorship to this result. It's part of the book, I guess.
My feeling is that this proposition shouldn't be so hard. I would suppose that it should be, I hesitate to say it straightforward, but
Yeah, it's straightforward, because in the C algebra compact operators, you have that. So essentially, that's how his proof is just I'm counting the number of lines, about 5-6 lines proof.
okay.
Okay.
Okay. So this should be
It's on,
standard. Okay.
now in page 104 of the book there.
Okay.
Okay.
Okay, thank you.
Let's move on, yes.
Yeah, okay. And likewise, for the C-star algebra, for the Leavitt path algebra also, this statement was proved in the book by Abrams and Molina. Again, I'm putting 2017, but it was proved actually earlier by I forgot who, maybe Abrams and Aranda Pino. Namely, it says that if an ideal I in a Leavitt path algebra is generated by a set of matrix units, E alpha and beta belonging to the index at lambda, then I is isomorphic to the matrix ring M sub lambda of K, consisting of all square matrices whose rows and columns are indexed by lambda, and which have at most finitely many non-zero entries there. Okay, so you see again a simultaneous same graphical property. What's surprising is both for C-star algebra and Leavitt path algebra very parallel, same type of conclusion. You are able to get it. So with that in mind, now we are ready to reach state our main theorem. Let E be an arbitrary director graph and K be a field. Then the following statements are equivalent. C star E has exactly one unitary equivalence class of irreducible representations. The corresponding Leavitt path algebra has exactly one isomorphism class of simple left also right modules. The graph E contains no cycles, no infinite emitters. The vertex at E0 is downward directed, and it is the hereditary saturated closure of a line point. And the Leavitt path algebra in this case is isomorphic to M sub lambda of K, which is the matrix ring of square matrices having lambda whose rows and columns are indexed by a non-empty set lambda, and which has only finitely many non-zero entries. Okay, and in this case, the C-star algebra is isomorphic to the C-star algebra of compact operators on a Hilbert space H, which has the set of lambda as the orthonormal basis there. Okay, so that's a complete answer to Naimark'S problem there. But if you look at the condition on the graph, you see there are only essentially two types of graphs for which the corresponding C-star algebra satisfies Naimark's property, namely either the graph E has no cycles but has a sink W, and all the paths in E end at W, or the graph E again has no cycles but consists of just a single tail equivalence class P of a infinite path P such that the source of P is a line point there. So pretty restrictive in nature. And just the example for this is the case when you have a sink W. There is an example where of a graph where all the paths may not be finite. They could come infinite also, come in join with W eventually. Or the other case where you have a line point, there is an example where you have the infinite path starting with V, and all the other paths essentially come and join, become a tail equivalent to that.
Yep.
So in the graph algebra case, I think really restrictive, so makes it very easy to reach the conclusion there.
So it seems to me that like example 2 is a subgraph of example 1 is a subgraph of example 2, right?
No, or a subgraph, yes.
But you need to have an end and sink, because the W doesn't emit any further. So we need to have a final end point, whereas here it's an infinite. It keeps on going. So I'm not sure whether W can be made a part of this because it's a sink. So this graph has a sink, which is a W, whereas here this graph has no sinks. Every vertex emits one edge at least.
And can we have like infinitely many edges coming into a given vertex? Ending at a given vertex?
Any number of them.
Any number of them, okay.
Can come and join any number of them. I just made a simple one, but yeah.
Yeah. It's hard to draw infinitely many edges, yes.
Yeah.
Okay, that's what I thought.
Yeah.
So no infinite emitters, but possibly infinite receivers.
Yes, that's true. That's very true. That too. I know some people use the direction of the arrow in another way, but anyway.
Yeah, like Rayburn, yes.
Yeah. I would like to next consider the case where C-star algebra has more than one equivalent, but finitely many or countably many non-equivalent irreducible representations. Okay. In that case, let's consider this case of C-star algebra. In that case, again, we have these. I'm resting on the shoulders of all these stalwarts, which enable me reach the conclusion easily. They did all the hard work, in my opinion. So here is a case where Bates, Pass, Rayburn, and Szymanski, please pardon me for my incorrect spelling instead of pronunciation of Szymanski.
Everything is fine, yes.
Okay. It says that suppose you have a graph contains a cycle without exits, say C, and if J is a closed ideal generated by the projections corresponding to the vertices on C, then J is Morita equivalent to the algebra of continuous functions on T, where T is the unit circle. And because C of T has uncountably many irreducible representation, this ideal J also will have an uncountable number of irreducible representations, which are pairwise, which have pairwise distinct kernels there. And these extend uncountably many irreducible representations on the C-star algebra, entire C-star algebra, C-star.
As a quick question.
Yeah.
How it is possible that this J is an ideal, but the C of T is a unital C-star algebra? So
It's Morita equivalence doesn't preserve identity.
Okay. Of course. You can have two Morita equivalent.
Yeah, right.
One is unital, the other isn't.
But fortunately, it preserves irreducible representations.
Of course.
So, and it's a well-known fact that C-star, C of T has uncountably many corresponding to each point on the cycle. The evaluation map gives rise to irreducible representation. So So in simple language, if a graph contains a cycle without exits, then the corresponding C-star algebra has uncountably many irreducible representations there. Okay. So if we are looking at C-star algebra having finite or countably many, such a thing cannot happen. That cannot have a cycle without exits. So that's our that's a punchline there.
Excuse me, I have a question about the comment of Adams.
Sorry, say it again.
Can I ask my question?
Yeah, you can ask a question, but kill the echo.
Yes, I come back. My question is that
Well, you cannot use two devices with microphone.
Yeah.
Okay, let's go ahead because, yeah.
You got
Are
it?
you ready? Ali? Hello?
do you hear me?
Yes.
Yeah, I can hear you now, yes. Well, please ask your question or we continue.
Excuse me, do you hear me?
Yes, we can hear you. So please ask
my
your question
apologies
or
for
we
my
continue.
yes. My question is, Adams says that how J can be. He was mistaken to hear that J is isomorphic to C of T, and I think that he
Isomorphic,
Not
more
isomorphic.
equivalent, and this is
yes. So why it was amazing that J would be isomorphic to C of T. I mean that is your problem is a unital or non-unitalness of J. I mean, is it obvious that the J described here is a non-unital algebra?
as an ideal, it would be non-unital.
Yes.
Cannot have
Yes,
a
an
unit.
ideal can have its own unit, not the global unit. For example, consider C of T direct sum C of T. C of T direct sum C of T is a unital unital algebra, and each component has its own unit. So it would be interesting to focus on this J. Is it obvious that this J as an algebra is not a unital algebra? The unital algebra is its unit is not necessarily the unit of the total algebra.
Yeah.
So I wonder, is it obvious that J is not a unital algebra?
This is a very good question, Ali. This is a very good question. I like your question. Yes. It's non-obvious.
I don't know.
At least not to me.
It must be. Maybe some of the experts in algebra may recognize. I don't know, honestly. I cannot.
Yes, I see.
And you know, it might happen, Ali, I believe what might happen is when this cycle without exit is a disjoint part of a graph. You know, if the cycle is a disjoint part of the graph, then what you are saying will happen. Okay? But if the cycle is not a disjoint part of the graph, then I believe this will be non-unital in the sense you just described. Okay, and so yeah, that's my answer to your question. The situation you are describing, I believe, will happen if and only if the cycle is a disjoint part of a graph.
Yes, I see.
Okay.
Thank you.
Okay.
Thank you.
But it was a very good question. Thank you so much. Yeah.
Thank you.
Yeah.
Okay. Let's go ahead.
Fortunately, in our situation, this cycle, the ideal may not come at all because of the nature of the property that we have on C-star algebra with this property. So this would be useful using this. Anyway, countable here could be finite or countably infinite. then if this collection of unitary equivalence classes of irreducible representations of such algebra is countable, then the graph has no cycle at all, but it'll contain line points. The reason it has no cycle at all, I'm going to just point out. Easy proof, because suppose on the contrary there is a cycle C, the base of the vertex V. We know we already earlier noted, I'm sorry, it's a typo, the corollary 6, the typo. We already noted that if there is another closed path D not equal to C passing through V, then it will give rise to uncountably many equivalence classes of tail equivalent paths, which will then give rise to uncountably many non-equivalent representations. So if there is a cycle C based on a vertex V, there cannot be a closed path D having a common vertex with the C, okay? With C here. So in that case, let's consider all those, the set of all vertices U, such that there are no paths from U to V. Now this set is hereditary and saturated. Easy argument to justify this. So you consider this hereditary saturated set of all vertices U so that there is no path from U to V. You look at the quotient graph.
By which you mean a subgraph?
No, it's a quotient graph. Essentially, formally you define the vertices of this quotient graph as all those vertices which are not in H, together with those vertices B sub H include the, I didn't have opportunity to explain this.
Yeah, breaking vertices, yes. But
yeah,
still
breaking
it's
vertices, yes.
okay, yeah.
Okay.
But still it's not formally speaking a quotient graph because you are not making equivalence relation and identifying things.
No, at the moment you just look at the quotient graph as it is. There, if you look at the image of the closed path, the cycle C, C will have no exits at all. Okay? Because if C had an exit, that, how should I say that? Because the edges, the vertices that are how could I say? Yes, if there is an edge, you look at the range of the edge. That vertex V, since it is no longer part of H, there will be a path from the vertex V back to the cycle. So that will give another cycle having a common vertex with C. So that's the idea behind it. Is that clear what I'm trying to say?
Yes.
Because the vertices in the quotient graph, none of them have a every one of them there will be a path from there to the vertex V there. So since we have removed all the vertices for which there are no paths from into V, this cycle cannot have an exit there. Because that will give another closed path having a common vertex. But that's but then by the theorem of Bayes and others, then the corresponding C-star algebra of this graph will have uncountable number of, that's the previous uncountable number of, we'll have if there is a cycle without exits, then we'll have uncountable many irreducible representations, which is not possible in our hypothesis there. So this shows that the graph cannot contain any cycles, but there is another argument which I'm skipping here. It shows that it'll contain a line point, because if it does not contain a line point, again, the basic argument is that will lead to uncountably many. You can create infinite paths and countably many of them, which are not Taylor equivalent here. That's again will contradict the hypothesis. There are only countably many irreducible representation there. So the main conclusion is that if there are finite or at most countably many non-equivalent irreducible representation of a C-star algebra, then necessarily the graph contains no cycles, but it contains line points here. So using this, we can know there is our main conclusion here. How much time we have?
Okay. You have 13 minutes.
Oh, I have, okay. So the main conclusion here is that if the collection of unitary equivalence classes of irreducible representations of a C-star algebra is countable, then C-star E is the union of well-ordered ascending chain of closed ideals I0, I1, I2, I alpha, alpha plus 1, indexed by ordinals alpha less than a countable ordinal tau, such that for all alpha less than tau, the corresponding quotient algebra I alpha plus 1 or I alpha is isomorphic to the C-star algebra of compact operators of a suitable Hilbert space H alpha. In other words, it's a building, the compact operators are the building blocks of this C-star algebra. Some kind of a nice, at least algebraically, I look at this very nice structural result, like a composition series. The corresponding quotients are all compact operators, algebra of compact. The main idea of proof is an induction argument. Basically, you suppose C-star algebra has this property. We know by the previous theorem that it contains line points. So take a line point, let I1 be the closed ideal generated by this line point, and then you proceed. You consider Y2. Suppose you have, let me just go to the transfinite induction step here. Suppose gamma is less than tau, and suppose I alpha has been defined for all alpha less than gamma greater than or equal to 1. If gamma is successor ordinal of the form alpha plus 1, so I alpha has been defined. So let I alpha plus 1 be the closed ideal containing I alpha, such that I alpha plus 1 mod I alpha is the closed ideal generated by a line point in C star E in the quotient graph, in the quotient algebra C star E or I alpha. Because the quotient algebra C star E or I alpha will also have the same property as C star E, having at most countably many irreducible representations there. Okay. On the other hand, if gamma is a limit ordinal, you simply define I gamma to be a union of I alpha. So proceed like that. After a couple number of steps, you reach the whole algebra there. That's how you construct such a ascending chain of closed ideals there. Okay. Let me give some examples. Proceed. For example, here is the easiest of the example of graph system algebra having exactly two non-equivalent irreducible representations. Because of earlier theorems, all we need is two tail equivalence classes, different tail equivalence classes. In this case, very simple. You have infinite path P1, and the line points are essentially the vertices in the first top row. And you could, sorry if I could get this, my son showed me a way to highlight this. I'm not able to do it. But anyway, yeah, he gave me a pencil where I could use highlight it. But anyway, you get it. Look at the first row, the path P1. See, V11, V12, they're all line points. Let's take simply V sub 1, it's a line point. You take the ideal generated by, the closed ideal generated by it, and then you mod out the corresponding quotient graph would be essentially the second row, V21, V22, and so on here. And so the corresponding chain, in this case, you will get the ideal 0 containing the ideal generated by the closed ideal generated by V11, and it's containing the closed ideal generated by V21. That will be the whole algebra there. So it's chain of two conditions, chain of length 2 here. And you could get this idea, you could iterate it. For example, go one step further. Here is an example of a C-star algebra having exactly 3 unitary equivalent. Again, to get that chain, again, you can see that the line points are simply points in the top row, V11, V12, V13. And simply take the ideal generated by V11 and the closed ideal generated by it. When you mod out, the quotient graph would be exactly, looks like this graph with two infinite paths like that. And let I2 be the closed ideal generated by V21, and finally it's containing the ideal generated by V31, which will be the whole C-star algebra there. And you could iterate it any number of times. For example, you could have, here is the example of C-star algebra having exactly n irreducible, non-equivalent irreducible representations there. One could actually apply transfer-rate induction, keep on going until accountable. E1, En plus 1, and so on. E sub omega would be obvious choice on that. But you notice that, I forgot to mention this, all these are essentially the C-star algebras, they're all AF algebras there. It's kind of interesting to keep a note of that.
Sorry, could you repeat the last sentence?
Yes,
Can you repeat the last?
Yes, C-star algebra satisfying the Naimark'S property, having exactly one equivalent irreducible representation has to be an AF algebra. Okay. So it's a simple AF algebra. It cannot be, what is the opposite of this would be, I'm black out of the name, what simple, infinite, what is that called? Infinite, There are two types. There's a dichotomy in simple set algebra. One is AF algebra. The other is, I'm sorry, at my age, I suddenly forget that name. Super, is it not super simplicity? What is that called?
Type 1, maybe?
There is another name, another type of simple set algebras. They are called, pardon me, I think not super simple. Infinite, yeah, infinite simple.
Purely infinite?
The other type, I'm sorry, I just blanked out. Maybe some of you here remember it. Otherwise, I have to look at the book and see what they say. I think it's simplicity. See whether he has given a name for it. I think it's called infinite simple. Yeah. I think it's called infinite simple, where there'll be infinite projection, I guess, maybe. Anyway, in this case, it's only a AF algebra, so it will be a direct limit of finite dimensional algebras. I think that's what's called AF algebra, I think. Anyway, that's a nice simplification of the structure of such C-star algebra. As far as C-star algebra is concerned, this is what I want to mention. The corresponding statement for Leavitt path algebra also, it will be such a union where, in the case of Leavitt path algebras, I don't know, in C-star algebra, do you have the concept of circle? Algebra, we talk about circle, which is direct sum of all simple modules. So in the case of Leavitt path algebra, the corresponding Leavitt path algebra with countably many irreducible representation would be a union of circles, very similar to the chain that we had for the C-star algebras there. Okay. That's basically what I want to say as far as C-star algebra is concerned. And maybe I'll stop with that. And I thank you.
Okay, thank you so much. Let's thank our speaker. Thank you.
Thank you.
My first immediate question is when you look at these graphs E2, E3, En that you defined, what are the graph sister algebras of these graphs?
This would be union of finite dimensional, for example. This would be union of finite dimensional algebras there, basically. Each layer would be
Ali, please stop this echo. I mean, you cannot have two devices.
Yes, my apologies.
I can only say that each layer is a union of finite dimensional algebra. But from my algebraic perspective, I don't know. Otherwise, C-star-wise, I don't have any further intuition.
These will not be compact operators, no?
If we compact not each layer, each successive quotient would be compact.
Okay.
Successive quotient. I alpha
I'm
plus
happy.
beta. Okay.
Okay, since I started asking questions, let me continue. I have one completely, totally obvious question, which just begs to be asked. Namely, there are so many different generalizations of graph sister algebras, higher rank graph sister algebras, Kunst-Pimsner algebras, quantum graph sister algebras, labeled graph sister algebras. So how about proving Naimark'S theorem for any of these generalizations? Any thoughts about?
Oh, very good question. Yeah. Here, maybe people are experts may be able to answer that. Yeah, graph helps. This is mainly everything got simplified because of the availability of the properties of graphs. I don't know.
Okay.
Certainly, it's a very good question for higher rank graphs. It will be obvious. I have a good feeling that there may be some success there. The other type of I don't know.
Okay. I'm very happy. Anybody else wants to ask a question? You guys?
Maybe just a small comment on the question.
Go ahead. Mhm.
Like Kunst-Münster algebras also have something called the condition L for simplicity.
Excellent.
So maybe it's not very not difficult, but maybe it's not too irrelevant to have such a like Naimark'S problem for Kunst-Münster algebras in general.
Excellent. Yeah, very good. Topological graphs also.
Yeah, like
Okay.
that's just a subclass.
Okay.
Yeah,
No, this is very good. Thank you. Thank you, Atul.
good comment.
Mariusz?
Yeah.
No. Anybody from Zoom?
I have maybe one or two questions, but I'm afraid that it would be very basic. But I don't know whether it was said. Is it in general that the sister algebra of a graph is of type 1?
Yes, and it's nuclear.
Okay, it is always like this. Okay.
Mhm.
And the other question is the following. Since you gave those examples at the end of your talk, so before developing this whole machinery, it was not obvious how to construct a sister algebra, a graph sister algebra having this property that, for example, it has exactly 3 irreducible representations up to equivalence.
Yeah.
So it was not obvious, yes?
No, it was not. I think
Okay.
it's for a general sister algebra. No, it was not clear. I mean, no, at least none of the papers.
So I think that there was a mistake in the comment. Not all graph sister algebras are type 1. They are all nuclear, but they are not all type 1.
Okay, sorry. Mariusz corrected me. Yes. What I should have said is that all of them are nuclear, Adam, but they are not all of them type 1. Yes, right,
No,
Mariusz? Yeah.
no.
Sorry, I just.
Yeah,
Okay.
there
There are
are
no examples of non-type 1 graph sister algebras, yes?
yeah.
Can you give one?
So there's a condition where sister algebra is type 1. So I just don't remember the condition. But then you can very easily figure out the example.
So I have a follow-up question. So having in mind this theorem 19, does it follow that, okay, if the set of equivalence classes of irreducible representation is countable, then it is of type 1, yes? Since this collection of ideals is this the so-called decomposition series, and correct me if I'm wrong, but I assume that if you have such a collection of ideas, that then your algebra is of type 1. Yes?
I don't know.
I don't know myself. I don't know.
Sorry, but in this theorem that was on the slides where you have a circle with no exits,
Okay.
maybe then it's not type 1, right? Because you have uncountably many.
No, but commutative are type 1. So
This one is not commutative.
So from solely from this condition that you have uncountable spectrum does not follow that something is not of type 1, since every commutative sister algebra is of type 1 and you have plenty of them having uncountable spectrum.
Yeah.
I just don't know. So let's continue. Ali, do you have a question?
No, thank you. I'm happy.
Okay. Anybody else? People who board the plane to Sydney? Tomek? Michał? Anybody? Okay, so since there are no further questions, let us thank Ranga again for this very fascinating talk. Thank you so much.
Thank you. I appreciate
Thank you for your talk.
Okay, all right.